really, really don't know whether this is going to work or not. We'll go to Twitter. Oh, here I am. Here's my face. So it seems to be working. What are we going to do today? So I think I miss a bit kind of the more exploratory kind of stuff, kind of asking questions. And I kind of realized that I've been doing too much stuff that it's been more like community oriented, and I'm a bit selfish. So I really wanted to try to understand a couple of things that have been bothering me for a long time. So when I started the channel, I started with a couple of videos with D-Wave systems, and then I keep reading and hearing people saying it's bullshit, it's BS, but like it's not really clear to me, and I really wanted to kind of um, go go deep with it, right? And I think the culminating point for me was when I commented on a Chicago Quantum Post recently. Let's see, where was that? I don't know if Reddit is a good chat room for quantum computing, to be honest. Was it these? Oh yeah, these bullshit quantum check request. And so the quantum bullshit detector said like that's BS. A reason is like I found the tweet funny. It's like we're working to reach 1,000 YouTube subscribers in 2020. Please subscribe to our channel. Um, uh, what did I say? Yeah. So they basically say you can keep up with the research and the progress in their financial portfolio optimization, including with quantum annealing computers. Um, so there's kind of two things that I'm not fully understanding here, right? So let me just open some notes maybe, so I can keep track of these. So one is basically what is really what is really quantum annealing, right? I hope you guys can read these. So this is something that like I know more or less, I remember, but I'm not like sure either. Is this it, is this where the BS is? Where the BS is? So this is kind of a question. Another question would be, is portfolio optimization? Oh, what am I doing? Sorry. Is portfolio optimization uh, with quantum computer with the quantum computer at all like bullshit, right? Or is it like, or is it just D-Wave? I mean, there's a lot of questions that I want to answer, and I should probably keep those. Because, so there's the Medium article, which okay, I'm recording just a tab, so I'll open it up in a second. And then there's an actual paper called Portfolio Optimization of 40 Stocks Using a D-Wave Quantum Annealer. Maybe I should start here with a paper. Because when I ask for these, is like, hey, where are they comments? Where are their comments? Like did they comment? Where are their comments, man? I asked. Oh yeah, here exactly. So I just hate Twitter threads. It's not really. Sometimes they're not linear, and that kind of bothers me a lot because I tend to miss basically some of the replies. So they say, our first portfolio results favor our three custom algorithms: simulated annealer, genetic algorithm, and fat-tailed Monte Carlo. When lucky, in our tweet yesterday, our quantum answers underperform the 60 asset benchmark. I don't know what this means, though. The underperform. Does it mean that it's actually working, or so maybe I should just go ahead and try to read these first, the actual paper. I'll put it now in the in the tab that I'm that I'm like basically okay. So yeah, that's probably the best thing that I could do with the time that I have today. Try to get an understanding of this, but that's my goal, and I really want to try to spend some time on these. As I wanna, as I said, wanna really kind of get to understand. Oh, sorry, you guys didn't see what. Is there a way to have like notes on the tab or something? Should switch to actually recording the full screen maybe. I just didn't want to post process the video afterwards, and so um, maybe. Anyways, I wrote down the questions. What is really quantum annealing? Um, is there where the BS is, and is portfolio optimization with a quantum computer like BS or not? Like, and what does it mean for this to be BS at all? I mean, it's like yeah, you can do things right. Like it doesn't mean like if you're not aiming at getting something more just for some reason more efficiently than a classical algorithm, you just want to do it because maybe it's not about efficiency, but it's about like the actual end result. And I fear that's kind of where the portfolio optimization stuff goes. Is less about the efficiency. Um, it's less about the efficiency. I mean, based on my experience in this whole thing right now, it's really, really hard to justify that a quantum algorithm or to find sort of quantum advantages really in terms of speed. And so when it comes to portfolio optimization, I guess what you're looking for is you're looking for better models. So you're looking for something that works better than the classical models. Maybe because of the entanglement, maybe because of I don't know. Um, so like if this is where the BS is, like I'm fine with it, right? Like I'm all in for trying to understand or trying to play with things that might be just different in nature. Um, but if the BS is you know that that just doesn't work, then let's figure this out. Okay, so let me open the paper. So I hope you can see these. Portfolio, okay, so that's July 6th, 2020. Portfolio optimization of 40 stocks using D-Wave's quantum annealer. We've got introduction, validity of the formulation, classical methods, and using an annealing quantum computer. Okay. And hopefully we can reproduce these. I really want to go and reproduce these. Like, introduction, because I think they claim that. They claim that, it's everything reproducible. So I definitely want to do these. Although I might need access to D-Wave, which, to be honest, I don't. But like, let's see how far can we get. Introduction, blah blah blah, validity of the formulation, classical methods. Uh, Brute force, genetic algorithm, random sampling, heuristic approach, simulating it as a Monte Carlo using an annealing quantum computer, the optimal portfolio, blah 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 blah. Developing the QBO to number of assets in the portfolio. Affine transformations of the QBO. I guess this gets into the mathematics, visualization, metrics, blah blah blah. Okay, that can. Let's see. Okay, so and discussion and conclusion. So what can we see here? Can we see completion time by method? So they are claiming this is faster, or at least it seems like the completion time by method is smaller. I don't know what CQNS by method are. Classical versus quantum annealer computations. Quantum and classical. So the quantum lower is better. Okay, so the classical is better. Uh, okay, let's start from the beginning. Maybe let's get to the basis. Okay. Uh, yeah. Okay. So the abstract. We investigate the use of quantum computers for building a portfolio out of a universe of U.S. listed liquid equities that contains an optimal set of stocks. Uh, okay, so the goal is to build a portfolio. So you're picking a portfolio. You're picking basically out of a pool of assets. You're picking a portfolio that is optimal. I guess in terms of maybe some kind of return schema or something. I'm not an expert in in the stock market. So I might have to learn something extra here and there. Starting from historical market data, we'll look at various problem formulations on the D-Wave system. So starting from historical market data, we'll look at various problem formulations on the D-Wave system, hereafter called D-Wave, to find the optimal risk versus return portfolio, an optimized portfolio based on the Markowitz formulation and the Sharpe ratio, a simplified Chicago quantum ratio. CQR is a Chicago quantum ratio, and then a new Chicago quantum net score, CQNS. We approach this first classically and then by our new method on D-Wave. Our results show that practitioners can use D-Wave to select attractive portfolios out of 40 US liquid entities. Okay, so the goal, I guess, if you've got like 40 entities and then you're going to pick a portfolio of some, I don't know, maybe, 6 or 5 or whatever out of these, that it gives you an optimal return versus risk kind of. What kind of, so it seems like they're simplifying that. This is a bit, this is, I'm a bit cautious when I see this, right? A simplified Chicago quantum ratio. So they're simplifying something based on I don't know what this is, Markowitz formulation. I'm gonna open another tab because I'm not gonna see these, but if I find something useful. So, portfolio theory. Okay, so it's a whole like portfolio theory under this name. Risk and expected return. Okay, so there's basically some mathematical equations here. Let me show you these guys. So this basically, okay, so we should probably read through these as well later, try to understand whether this has any influence in the results. But like, okay, so they're picking a model, they're simplifying it. It's the, and then they run it both classically and good. And quantum. So the challenge we approach in financial portfolio optimization is to maximize expected returns while minimizing variability of expected returns or risk. So they define risk as the variability of the expected returns. This is a buy and hold strategy and not a meet or high frequency trading strategy. It relies on previous peer risk, and in our case, 1 year of daily adjusted close data, and the underlying variability and relationship with equities. We believe investors can improve their chances by selecting the right combination of stocks. Among the major challenges in financial portfolio optimization is how does an investor balance long-term investment versus between expected return and volatility? And this is why we tackle this question from a variety of methods. This problem is particularly well suited for an annealing solution. Either classical simulated thermal annealing or quantum annealing, since we wish to consider n equities in which each equity may be included in a portfolio or not. So this yields exactly 2 to the power of n possibilities. Okay, so for a potential list of equities as small as 40, this becomes nearly invisible in a workstation. When we approach the entity of the S&P 500, we very quickly run into solution space, which is computationally infinite. That is, we do not have enough memory in the observable universe to run through a brute force solution. This work is structured as follows. Okay, so there's some exploration with the Sharpe ratio, where beta is the ratio of covariance of a portfolio with the market over blah, blah, blah. Okay, so this is then details on the actual model. We'll come back to these in a second. From here, we develop a Chicago quantum ratio. Okay. And it's the covariance of the ith asset against the entire market. This is a slight improvement over the Sharpe ratio in terms of computation, as we need not consider nominal assets. Okay, so these index simplifies the computation. That's what they're claiming. We can also reformulate CQR in matrix form. We explore this form. Okay, so they go ahead and do a matrix form of the CQR, which I guess may be applied. No, but that's maybe too gate model-ish, like applied to a state, or if, I don't know what they want to do with the matrix. We explore these formulations by a variety of classical methods. This, however, causes some different set of mathematical problems in formulating a consistent quadratic form. Finally, we settle on the Chicago quantum net score, which is given by. Okay, so it seems like they've got some trouble adapting the mathematical formulation to fit into the D-wave stuff, and so they adapted. And then, okay, validity of the, we'll dig into this later. I'm just really going to fly through in this first video. Validity of the formulation and its current capacity D-wave solves problems which are formulated in terms of an Ising model. Thus, our practical challenge is to provide for D-wave an acceptable model on which it may begin its computations. Consider following image. Image 1. Where's image 1? Here. Comparison of CQR and CQNS scores against the Sharpe ratio. But what are you comparing? I don't understand that. Our formulation has a propensity toward conservative side in investment terms. However, it also demonstrates that the present formulations are near the efficient frontier of investment portfolios. Thus, from an empirical perspective, this formulation passes muster. We developed the method in more detail. Okay, so this is basically what they're saying is the method makes sense, but we can dig into this later as well. The classical methods. So it does seem like they're trying to use indeed the D-wave system here is for tractability. Like, so they say for 40 portfolios you cannot just brute force these because you've got. So I'm guessing the idea here would be you go through each possibility, you calculate whatever ratio you're using in your model, and then you just sort those and pick the top 5, right? That is of course intractable with 40 because you have 2 to the power 40 possibilities, so you cannot just brute force it. And the claim here is that the D-wave system can do these because I've got to pause for a second. I'll be back in a second. You won't notice the difference. Okay, so I'm back. You probably didn't notice, but I just took some time off. It's a couple of other things to take care of. But anyway, better this way maybe. So what I was going to say is it seems like the issue here is, or they're trying to use the airport to sorry, the airport. I'm at the airport, but they're trying to use the D-wave system to basically be able to actually do something, right? Because the 40 portfolio, the brute force is non-doable. So here's a brute force discussion. The smaller asset universe are able to loop through the all binary solutions and then brute force roughly 40 assets. But that's not possible. There's a generic algorithm. Okay. Gets to a local minimum deeper than our Monte Carlo method with 950 million samples, and does so very quickly. Our difficulty is in tuning the parameters for number of evolutionary steps, probability of elitism, and size of initial population. Even with essential random guesses at these parameters, our generic algorithm reaches a low enough energy level so that we can determine whether the quantum annealing solution. So we can determine whether the quantum annealing solutions are legitimate. Okay, so here what they're saying is that with the generic algorithm, they can at least get something comparable, like they can compare with the D-wave system output to at least check whether the D-wave system is not like BSing or something. Random sampling, as mentioned earlier, is slightly more than a workstation can know without an in-place algorithm. Just randomly sample as much as we can. We're able to sample roughly 2 to the power of 29 portfolios of potential 2 to the power of 40. This means most of our effort is spent around portfolios of size 40 plus minus square root of 40 percentage-wise. This doesn't cover much of the entire spectrum, but we approach 0.4% of the mid-size portfolio. Okay, I don't know. Okay, heuristic approach. But what's the point of using the D-wave system then at all here? The original test of our problem comes in the form of simulated thermodynamic solution Using statistics of random matrices, we're able to tune in the parameters of our simulated annealing solution to deliver very deep local minima. Additionally, this style solution only covers minimizing risk in the portfolio based on the cooling rate of the thermal annealing. Okay, so using an annealing quantum computer, the optimal portfolio in our case is one which maximizes the Sharpe ratio. However, as presented, the Sharpe ratio of a portfolio is not computable as a QBO. So then they have to basically, the main thrust of this research is in fact, okay, so okay. So the challenge is to formulate it in a way that the D-wave system can eat it. Blah, 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 developing the QBO. We'll get into the details later on. I'm just flying over things right now. Because the point is, like, if they have to do some simplifications, we'll see the results. And I'm definitely, we're really going to replicate that. Embedding, scaling, and hardware considerations. Until the terms both variants are true from yours inspector shows how the system encodes and embeds assets into physical qubits. An attempt at changing the formulation by manually embedding terms to respect the reordering of assets does not yield substantial improvements. Affine transformations of the QUBO, and explain portfolios of different sizes we presented a different matrix to D-wave for each desired size of portfolio. We add a penalty for exploring portfolios of different sizes while maintaining accurate values of the desired portfolio. The intuition for these follows closely from converting a QBO into an Ising model. This transformation, blah, blah, blah. Okay, so these are more technicalities. I think I'm going to sneeze. No. Visualization into landscape is critical in learning how the wave finds a solution. It also aids our understanding of how matrix transformations adjust the landscape to improve the probability of sampling correct asset values. Matrix CQN is calculated. If you place a penalty on the smaller portfolios by adding a shift term, subtracting a shift term places the penalty for larger portfolios. Okay, result, our experimental warfare is as follows. Download 1 year of daily market data for a specific set of N assets in indices. Current as of that moment, hold the data for all experiments, calculate covariance of each asset with the market, say how much this varies with the market in respect to the market, based on log returns, calculate covariance terms between assets, calculate underlying and summary values, including Sharpe ratio and Chicago quantum score for an all asset portfolio. Okay, so kind of hold all the 40 assets. Okay, so what they do is they, collect. Okay, so that would be the, yeah, because that's probably the worst. I mean, that's definitely the worst you can get. Like, just pick everything, right? And you want to pick a smaller portfolio that maximizes or minimizes probably the ratio. Right, the QBO for each portfolio size. QBO for each portfolio size. This I don't get. This part I don't get, but it's because I didn't get into the QBO representation part. But run a classical probabilistic algorithm, in our case, a generic algorithm to see one best portfolio and its values. Okay, so run basically one of the classical alternatives, so then we can compare it with the D-wave results. Execute the D-wave using appropriate range of portfolio sizes. Use the D-wave result to see the generic algorithm. Compare values to classical. Oh, so they use the D-wave to seed the genetic algorithm. Okay, these so they are not using the D-wave system to choose the portfolio, to choose the assets, but to inform the generic algorithm. The genetic algorithm. I'll have to go into details, I guess. The following figures, 34, give some idea of how well the quantum computer performs using the CQNS against the Sharpe ratio. We see that in the sample it approaches the efficient frontier in a few cases. Highest return for that level of risk. Most points achieved. One will also. What's that? Baby shouting. We see a DOF outperforms classical random sampling on average for all portfolios, which is where most of our portfolios were run. This shows that D-Wave is not picking randomly or average solutions, but good ones. D-Wave classical. Expected return for standard deviation. Babies. I don't know if you can hear this as a baby in the background. Discussion and conclusion. Positive semi-definite considerations. Practitioners of NumPy will know well that NumPy is prone to running errors. In particular, we find that NumPy computes covariance matrices with slightly negative eigenvalues. What? Okay, where's the code? So let's find the code. Next steps. References. Thank you. Where's the code? Maybe in the Medium article. So please see our archive article here on your preferred decision playlist here. Where's our class? Maybe if there's no code, I just should try to do this myself. So kind of based on the paper. Go back to the paper. What if I just search for these code? Is there anything in GitHub maybe? ResearchGate. Maybe in the web page. Oh, that hurt. So portfolio, contact team, block off, and security use cases more. Card logging, team block off, and security use cases. This two video options. Okay. GitHub. It's the Chicago Quantum maybe. Maybe there's something. No D-Wave portfolio. And it's just one repo. Quantum Markovits and D-Wave sample code. Could this be the... Could this be the... Who's this user? So data, averages, covariance prices. Is there anything in the code? Code reads embedding composite. Okay. Could that be the code? Who's this person? And who... I don't know if this is the course of operation. I don't know whether this is these portfolio D-Wave. Sorry, I've been checking. I was checking other tabs. I'm apologies for this. I started the video like that, and I can't change the. I guess we maybe can just start working on these. To be honest. So is there enough detail? I guess this basically. So here there's the formulation, right? So they say we can reformulate CQR as in matrix form. We explore these formulations of classical methods. A D-wave requires a linear quadratic form. We attempt to rectify this by exploring the following, which I don't understand, and I mean I really don't understand. Um, mm, but I don't understand one thing. So so what are they calculating with the D-Wave computer? So RW is a weighted portfolio, and alpha is a real number, and most experiments we choose an equal weighting. Brute force, genetic algorithm. Oh, genetic algorithm solution gets a local minimum deeper than Monte Carlo method. Random sampling, heuristic approach. Mm. 1 second. Yeah, I running out of time, but I'm trying to understand this. So I'm trying to understand where they are calculating with the QBO, the main for not cases which makes sense the Sharpie range, however. Sharpie is not computable. So they're trying to thrust this research is in fact how to formulate a QBO, which, when presented to D-Wave, pretty similar to the classical Sharpie ratio. So they're calculating the actual ratio. Or the numerator can be expressed as a simple dot product where we expect the return and the relative weight of the ith acid respectively. The denominator. Okay, so the D-Wave computer is supposed to give a weighted, like an answer of like the weight of each of the portfolios that minimizes that ratio. And still they use these as a starting point for the generic algorithm later. Maybe. Keyword to number of assets in the portfolio. This is what I don't really get. When dealing with a single asset portfolio, we only consider linear terms in the cubo and triangle matrix. I think I have to, so D-Wave, cubo. I think I have to go through these first. Maybe try to get something there up and running. That's what I'll do in the next video. Stats for quadratic and constrained binary optimization is from science for true or false. The cube is defined as an upper diagonal matrix. This can be expressed more concisely. Okay. States terms quadratic coefficient variable. Graphs. But what's the way that D-Wave define an objective function, objective value, Q1, I guess Q0, Q1 being the qubits, and then, so I'm guessing what they're doing is kind of define that ratio as the function, and then as a function of like different portfolios, and then try to kind of get the okay, so each qubit will be an asset probably. I guess that's the point. And then you want to have the 40 assets represented, and you want to get an answer of what's the probability associated with each asset. I guess that's what you want to do. But I don't get, like, one thing that I'm missing here is how does these then feed into the genetic algorithm? Genetic algorithm gets to a local minima deeper than our Monte Carlo method, and does so very quickly. Our difficulty is in tuning the parameters for a number of evolutionary steps, probability of altitude and size of potential population. It was essentially random guesses at the parameters. Our genetic, which is low energy level, developing the QBO, embedding scaling hard considerations, into the QBO. Because I don't get that step. Like, I don't get that, like, around a classical. So execute the D-Wave using appropriate range of portfolio sizes. And use the D-Wave to seed the generic algorithm. This is what's not clear. Like, I get maybe the D-Wave is used in here to work around the brute force, or the fact that you can't just brute force the thing. But that doesn't still give you an optimal. Yeah, I don't know. It feels like there's some pieces missing here, so I need to find more about these in terms of what are the other, like, is there any reference code anywhere that I can take a look at? Otherwise, like, I can, what I will do is I'll try to implement the D-Wave stuff they talk about in here. And then, but I really don't know what the genetic algorithm is that they're using, and how does these. So we further give results of the CQNS by method. Once one will notice that D-Wave performs well, in fact, obtaining better results than Monte Carlo methods, but underperforming the genetic algorithm. Using D-Wave as a seed guarantees that the genetic algorithm will perform better. Okay, so that's the reason. As we disallow anything worse than the seed to propagate through generations of solutions. Okay, yeah, so it's basically. Okay, so you create an initial population based on what D-Wave tells you, and then you tune the actual you tune the actual genetic algorithm not to go worse than these, and so you can only get better. Okay. Yeah, I don't know. I don't even know whether you can call this BS or not BS, or like, where is the problem in here? I'm a bit like, to be fair, it's like, I don't know where. I really don't know what is there to evaluate at all. It's like, it feels like they're using the D-Wave system just to get a better first guess. And it's maybe less about efficiency, but it's about the quality of the guess, right? If it's about the quality, I don't think that's BS. But like, if it's about efficiency, yeah, that's another level. It's a discussion at another level, I guess. But I don't know. Let's try to implement this, okay? And then we'll get conclusions at the end of everything. So we'll see. Yep, gotta go. Bye bye.